This simulation is going to help us to understand the idea of resonance. So here we have 4 blocks. They all have the same mass, 1 kilogram. So all of these have a mass of 1 kilogram, but they're each tied to a different set of springs. So the first spring has a stiffness of 100 newtons per meters. The second one has a stiffness of 200 newtons per meters. The third has a spring constant of 300, and the fourth 400. And we're going to make this thing vibrate, and we're going to see how the vibration of this base here is transferred to each of these different objects. So now let's go ahead and increase the frequency. So what you notice is that the mass 1 here is vibrating a lot more than the other ones. The reason why is because the frequency of this box or this driver matches the frequency of this first spring here. So that means that it's able to transfer more of its energy to the spring, and that makes that one vibrate more. So resonance has to do with the fact that you have a driving force that vibrates at one frequency, and if the frequency of the driving force matches the frequency of the thing that's feeling the force, then the object that's feeling the force is going to have a large amplitude when it vibrates. And let's go ahead and increase. But if you notice these other ones here, they're not vibrating. So let's go ahead and increase the frequency. So you can see it there. This is actually closer to the resonant frequency of mass 1. It has the highest amplitude because, so we can say here that the resonant frequency for mass 1 is going to be around 145 hertz. Let's go ahead and increase our frequency more. Well, actually, there you go. This is getting closer and closer to resonance. So this is probably closer to the resonant frequency of mass 1. But notice now that once you've gone past the resonant frequency, so it's not about how high the frequency is, it's about the right frequency. So now that the frequency of the driver is not equal to the resonant frequency for mass 1, it's not vibrating as high anymore. But now let's see how if we can get the resonant frequency for mass 2. So you notice mass 1 is vibrating less and mass 2 is starting to vibrate more. So let's see if we can find the resonant frequency for mass 2. That's probably getting close to it there. So that's probably close to the resonant frequency for mass 2. So you notice this is at a higher frequency now. But still, the concept of resonance is that you have two things. A driver that's vibrating at a specific frequency, and the object that feels that vibration. And if the frequency of the driver matches the frequency of the vibrating object, then they'll be in resonance. And because they're in resonance, it's going to vibrate at a higher amplitude. But if now the frequencies don't match, so this is probably closer to the resonant frequency for mass 2. So it has the highest amplitude of vibration because the frequency for mass 2, or the driver, matches the natural frequency for mass 2 here. What if we increase our frequency more? You notice that it stops vibrating. So it's not about having a higher frequency, it's about having the right frequency. And that right frequency is called a resonant frequency. Let's see if we can find the resonant frequency for mass 3. I would say that's probably around that right there. So this is saying that the driving frequency for mass 2, or the natural frequency for mass 2, is 2.78 hertz. So if the driver vibrates at the frequency such that it matches the natural vibration for mass 3, it's going to be able to transmit its energy efficiently to mass 3, and it's going to cause it to vibrate at a really high amplitude. So this is the concept of resonance, that the driving frequency has to match the frequency of the driver has to match the natural vibration frequency of the object that feels that force. So here, there's another term that you might hear about, which is the idea of a pulse. And pulse means just that you add up a whole bunch of different waves. So you add up a wave that looks like this, and a wave that looks like this, and a wave that looks like that. And you actually create a small wave. And you can use this to send signals. So another application is sound canceling, noise canceling headphones. We can use destructive interference to cancel out the sound from the outside. But also, for transducers, you can actually use what I just mentioned to actually not just to create images, but to direct the beam from a transducer. So this is your transducer here, and how it works is that you have a bunch of little sound sources, and each source sends their own wave. And you can synchronize the sources, so in some places they add up, in some places they cancel, and you can actually create a beam to make it to have a particular shape, so that it's going to be most intense here and less intense in other places. And you can actually use that to direct the beam, to make the beam move forwards, sweep side to side. So you can use the beam, you can use the fact that you're sending out different pulses at different frequencies, and you can make them cancel with each other in some places and add up in other places, and effectively you can steer the beam to look at different parts of your patient. So here, the last part has to do with, these were about how to operate, how we can use sound to make transducers operate. These next two components would be what makes you get a bad image. And it's the idea that when waves pass through a barrier, they tend to bend around corners. So like, for example, if these were just billiard balls here, they would all move in a straight line. But waves actually tend to warp or bend around corners. And that tends to cause distortions. So this idea of waves bending around corners is called diffraction. So something else that it's an interesting application, but it causes distortions, is the idea of beats. It's when you have two sound waves that are pretty close to each other. For example, in 1 second, this first tuning fork is going to vibrate 438 times, and the other one is going to vibrate 440 times. So they're pretty close in terms of the vibrations, but they actually cancel with each other in some places, and they'll add up with each other in other places. So I won't be able to play this video because I don't think I'm going to be able to play sound, but I recommend that you listen to what the beats sound like. It's like a wobble in the sound, and that also causes distortions. Something else about waves is that waves don't last forever. So ideally, you imagine that a wave goes on forever, but the truth is, because of friction, waves tend to die down. So another concept that you talk about is the fact that a wave's height decreases with time, and this is called attenuation. So we're going to stop here for chapter 16.